All right, it's a pleasure to welcome everyone here and all of you online to the second Minerva Lecture series of the term. The Minerva Lectures have been made possible for the last 10 years by generous funding from the Fernholz Foundation, and that's made it possible to bring in people to tell us about some of the most exciting developments in mathematics. And so since that's what we're here for, without further ado, I will turn these proceedings over to Bhargav.
Great, thank you. Thanks a lot for the invitation again, and also for showing up on Friday evening. Right, so last time I talked about prismatic homology, and I tried to give a little bit of an idea of what the problems that motivated the theory were, and what the shape of the output looks like. Today I want to talk about prismatic crystals. So before I get into what that is, let's just set some notation up. So it's going to be similar to last time, where I have fixed my prime p once and for all. I have the ring of p-adic integers, and then I have something nice over it. So let's say smooth and projective. For the experts, really all I need is that X could be any p-adic formal scheme. So actually most of what I'm going to say is already interesting today in the case when X equals ZP. So there's somehow no geometry in the situation. It's all about the arithmetic. So that would also probably help people that are not algebraic geometers to follow what's going on. Right, so I want to talk about prismatic crystals. So prismatic crystals are essentially the natural notion of coefficients for the theory of prismatic homology. Whenever you have, like most kinds of homology theories come with their own sort of attached notion of coefficients, these are the objects you can take the homology of. So for example, in singular homology, you can take singular homology of any local system, with coefficients in any local system, which is a representation of the fundamental group of the space. And this is very useful, for example, if you have a fibration x to y, and you're trying to relate the homology downstairs to the homology upstairs, you naturally run into the singular homology with coefficients in a local system. Similarly, for Rham homology, if you have a vector bundle with a flat connection, you can write down as the Rham complex. The flatness of the connection is exactly the condition you need to do that. And then talk about its homology, which is the Rham homology with coefficients. And so I want to talk about the analog of that operation in the setting of prismatic homology, but I won't actually focus on the homology of those objects. I'll just focus on the objects themselves. So that's what prismatic crystals are. Okay, so that's where we're headed. Now I have to actually get my hands dirty and give you a definition of what I'm talking about. So far, I've managed to avoid doing that. And so let's, in order to define prismatic crystals, I first need to tell you what a prism is. And so let me start there. So this notion of a prism was discovered maybe, I don't know, like 5 years ago. And it's sort of what makes a lot of what I'm going to say work. It's only, well, let me just write it. So what is a prism? So a prism is a pair A comma I, where A is a commutative ring. It comes equipped with a little bit of extra structure, and that extra structure is very important for what happens later. So it's not just a commutative ring, it's a commutative ring equipped with a lift of the Frobenius endomorphism. So phi from A to A is an endomorphism of the ring, which reduces modulo P to the Frobenius. I guess I'll continue with lifting Frobenius, meaning the P power map on A mod P. And then this I is an ideal which interacts in a specific way with the Frobenius. So I is an invertible ideal. Invertible just means, so if you don't know what this means, just pretend that it's generated by one element, and the element is a non-zero divisor. So it's kind of the simplest kind of ideal you can have in a commutative ring. And they satisfy these two conditions. So the first condition is the mild completeness condition, which is A is, I'll say it's P comma I complete, which means you're allowed to make sense of formal power series if the entries of the formal power series, so the variables are taken to be elements of bigger and bigger powers of this ideal. And the more important condition is the prismatic condition, which is about the interaction between I and phi. And the condition is the following. So there are various ways to state it. I'll state the easiest one to understand. So any local generator of the ideal, so local because I only demand it to be invertible rather than free. So any local generator D inside of I satisfies the following property. So I can take my Frobenius endomorphism, or the lift of the Frobenius, apply it to D, and since phi is supposed to lift the Frobenius on A mod P, I know that this expression has to look like D to the P plus P times something, and the condition I'm demanding is that it's P times a unit. So this is kind of the key point. Geometrically, what this, so if you're thinking algebra geometrically, what this is saying is that the divisor defined by I and the divisor defined by its Frobenius translate meet as transversely as possible. So it's some kind of a non-degeneracy condition. Okay, so that's the definition. The precise details are not going to matter that much. Yeah. Why the word prism? Can I come back to this at the end of the talk? It has to do with my musical choices, sort of. Right. So it's not at all clear from the definition why this is good for anything. And I'll try to give you some ideas why later. Maybe for now, I just want you to take away that there is a ring with a Frobenius lift, and then there is an ideal, and then there's some relation between them, which is not going to be that important for this talk. And so here are some of the main examples to keep in mind. So the most basic example is you just take the ring of p-adic integers itself, take the ideal generated by P, and phi is the identity map. So the identity on FP, on ZP mod P, which is FP, is also the Frobenius by Fermat's little theorem. So the first condition is satisfied, and then you can convince yourself that these conditions are also satisfied. So each time you have a prism, there'll be an attached cohomology theory to it. This is the prism that leads to what's called crystalline homology, which we don't want to discuss. The second one is the prism that leads to the theory I talked about last time. So you take formal power series in a variable u over the p-adic integers, and then you look at the ideal u minus p with Frobenius defined by the condition that phi of u is u to the p. And so, okay, if you are bored, you can just try to prove that this satisfies this condition over here. So taking d equals u minus p, you get a unit when you write out phi of d, like so. So this is the prism that corresponds to the cohomology theory that was mentioned in last time's talk, this kind of theory that interpolates between singular cohomology and Rham cohomology with mod p coefficients. And then finally, I just thought I'd mention this because this example was somehow one of the first indications that this was a good definition. And so it's the following idea. So if you work with prisms which are called perfect, meaning the Frobenius is actually an isomorphism. This map over here. Then it turns out that this is actually a category which has an alternative description. in terms of things that were known to be useful in p-adic Hodge theory. So this is the same as the category of perfectoid rings. And the construction is you take a comma I to a mod I. And so this is an equivalence. And so through this equivalence, you can regard the notion of a prism as being some kind of a deperfection of the notion of a perfectoid ring. Perfectoid rings have to do with rings where Frobenius is an isomorphism. And if you want to relax that condition, this is a candidate. Is that okay? So I apologize, the first 15 minutes of this talk are going to be me throwing a bunch of definitions at you. But once I have those definitions, I'll be able to tell you something interesting about what they do for you. So again, let me emphasize, please feel free to ask questions at any point. So it's an invertible ideal. So it's like a line bundle. It's only locally principal. Yeah. Sorry, for the Zoom audience, the question was, what is a invertible versus having an actual generator doing for you? Other questions? Okay, so the contention is that having this notion of a prism allows you to attach a bunch of invariants to our X. And so the mechanism by which this happens is the following. So there's something called the absolute prismatic site of X, which is I'm going to denote by X prism. This is kind of some of the key player today. I'm just going to think of it as a category. So you can ignore the word site there. And it's given by the following pieces of data. So you have a prism. And it has some interaction with X. Namely, you're given a map from not the prism to X, but rather the face of the prism. So A mod I into X. So I'm using some algebraic geometry language here. And so I think of this as a prism that lives over X. And I'm going to use this to define some invariants of X. And again, if you sort of don't know, if you're not an algebraic geometer, just pretend that X is spec ZP, in which case the second piece of information is no information at all. So this can just be ignored, and I'm literally looking at just the category of all prisms. No, it's just a morphism. Yeah. I'm sort of trying to probe X using prisms only. So instead of working with all spec of all rings mapping to X, I only work with spec of rings of the form A mod I, where A is a comma I is a prism. So it's some construction. I mean, it's not all clear right now why this is a good idea. But I'm going to use it as a device to define invariants. And so here's kind of a typical example of how this goes. So I'm going to use X prism to define new invariants X. And the first example is what's called prismatic homology, or really it's absolute prismatic homology. It's slightly different from what I talked about last time, but very much in the same ballpark. And it's defined as follows. You take an inverse limit over this category of all prisms over X, so over the absolute prismatic site, of the ring A itself. And so you have to interpret this in some suitable homotopy theoretic sense to get a chain complex rather than just a single abelian group. But formally, it's a very simple construction. You just take an inverse limit indexed by this category of some natural functor on this category, and the functor on this category is just remembering the A and forgetting everything else. Is that okay? So essentially, this is what I did last time, except instead of working with the absolute prismatic site, I only worked with those prisms that live over this fixed prism, ZP of U, comma U minus P. And that gives me this cohomology theory I was talking about last time. Today, I want to focus on the absolute theory, so let me not give a name to the other one. And so this is kind of how you extract cohomology or chain complexes out of this category, which is defined using the notion of prisms. What I want to do now is I want to talk about crystals. So these are the coefficients for prismatic homology, and it's going to follow a very similar looking approach. And so here's kind of the main definition, which is the definition of prismatic crystals, and it goes as follows. So it's vector bundles on, so that's this notation. I will refer to these objects as prismatic crystals. On X, and it's going to look very similar. It's the inverse limit over all objects of this site. But now instead of taking the inverse limit of A, I'm going to go one categorical level up. So instead of working with the inverse limit of A, I'll have the inverse limit of a category attached to A, which is the category of finally generated projective A modules, or vector bundles, as I'll refer to them. So in other words, concretely, this inverse limit is not that hard to understand. What you have to do to prescribe such a prismatic crystal is, for every prism over X, I have to specify a projective A module. And then if I have a map between two prisms, the A comma I to B comma J, then the module I have over B should just be the module over A, scalar extended to B. That's what this inverse limit notion spells out to, if you try to write out how an inverse limit works. Okay, and then the second definition, which I promise you is my last definition before I can actually tell you something interesting, is just based on the observation that I didn't need to put an A over here. A was varying in my category, but so was A mod I, because the ideal was also varying. And so I can also do analogous crystals with coefficients in A mod I rather than in A, which I'll call Hodge-Tate crystals. Okay, so, or Higgs crystals, actually, sorry. Okay, thank God I'm done with my definitions. So again, if this was too much of notation to start with, just forget about it. Just remember that attached to X, there's this category of prismatic crystals defined using prisms, and there's a category of Higgs crystals also defined using prisms. And that's sort of an obvious map from one side to the other by basically tensoring an A module with A mod I to go from the left to the right. And the goal of this talk really is to tell you that, okay, so this is some definition you concoct using this site, and it actually is capturing something interesting. And so I'm going to try and unpackage what this information is saying in much more concrete terms. No, so what you get is called Hodge-Tate homology. It's also not classical. But there's a variant of that which would give you crystalline homology, which would be classical. It's a little. So if you only work with crystalline prisms, so prisms A comma I where the ideal is generated by P, then you would get crystalline homology. Okay, so maybe I should just say one example of these objects. So essentially, for any reasonable notion of coefficients for a cohomology theory, at least in algebraic geometry, you want the following stability property, that if you have a nice morphism, let's say a smooth projective morphism from Y to X, there's some notion of a constant object upstairs, and its push forward should give you interesting objects downstairs. These are called, like in various settings, are called, for example, the Gauss-Manning connection in Rham cohomology is an example of this. And so the same thing is true over here with some small stars. So Y to X is a smooth projective map, meaning it's the algebraic geometry analog of a submersion. Then there are these Gauss-Manning crystals attached to it. So you can take, I guess maybe I should have said there's a constant crystal first. Sorry, let me do that before I write this. So the assignment that takes a comma I to a. Right. So to specify an object of this category, I have to specify a compatible system of finally generated projective A modules for wearing a comma i's. I can just take A itself, and that is going to satisfy everything I need it to satisfy. So this is an example of a crystal, and it's called the structure sheet. And so this one is called O prism, which is also where my notation over here came from. And then the second example is that you can sort of push this around whenever you have a smooth projective morphism. So F from Y to X is smooth and projective. Then these push forwards are usually prismatic crystals. So let me put a little star over here. The star is there due to torsion phenomenon. So essentially, you want to be a prismatic crystal, you need something to push forwards to be a vector bundle. If as you move in this family, there's extra torsion in the cohomology of some fibers, what you get won't be a vector bundle downstairs, but will just be a module with some torsion at those points. And so it's not quite a prismatic crystal in this sense, but there's an enlargement of this notion where it does live. Right. Okay. Great. So far I threw a bunch of definitions at you, and I told you that this category that I've defined has at least some objects of interest. Namely, there's the constant sheaf, and there are these push forwards. What I want to do in the rest of the talk is just spell out what this category looks like, or really what the relation between 1 and 2 looks like when X is the spectrum of ZP itself. And there you get some interesting connections to arithmetic. And hopefully that'll motivate what's going on. And so I want to do this through 2 analogies. So I want to first recall Vase analogy between number fields, or number rings really, and Riemann surfaces, and use that analogy to motivate a theorem on the prismatic side that has a counterpart on the topological side. So. And then I'll also give you an application of this, which is extrinsic to the prismatic stuff. So Vase analogy with Riemann surfaces. Okay, so probably a lot of people in the audience have seen this before, but I know there are some students. So let me try to draw a table. So here's the geometric side, and here's the arithmetic side. So I'm going to just focus on the simplest case. So the integers. And then on the geometric side, that corresponds to a Riemann surface, C. If you like, it's a complex algebraic curve. So it's the analog of, it's the geometric analog of a ring of integers of a number field. And really, since I'm talking about spaces rather than their rings of functions, I should put a spec. So it's spec Z is really the arithmetic counterpart to C. The points of spec Z are given by the usual prime numbers inside the integers, together with one funny point, which we'll ignore. And so if you have, in particular, we have a distinguished point, which is given by the prime that we fixed. So spec of FP. And so that corresponds to, on this side, to just fixing a point in the Riemann surface. And then in between them, we have the object that we were talking about in these talks. So give myself some space. So I have spec ZP over here, the p-adic integers. And spec ZP is the sort of arithmetic counterpart of not quite the Riemann surface, but rather a small neighborhood of this point on the Riemann surface. So it's like a formal disk around this point. Okay, so this is a disk. Okay. So this is the analogy. And then in this analogy, what I want to do is tell you what the relation between 1 and 2 looks like on the geometric side. So over here, I have these prismatic crystals. And then I can sort of tensor over A with A mod I, and I get these Higgs crystals. And I want to explain what the counterpart of this is on the geometric side, and then I'll tell you a little bit more about what this category over here looks like once I tell you what the geometric counterpart is. Let me actually leave this board to finish this table. So the geometric counterpart of prismatic crystals turns out to be the notion of a lambda connection. This is something that was invented by Deligne in understanding the work of Carlos Simpson in non-abelian Hodge theory, but it's a rather simple notion. So recall. So it's a deformation of the notion of a flat connection on a Riemann surface. So a flat connection consists of a vector bundle together with some ability to differentiate the sections. In a lambda connection, there's an auxiliary parameter lambda, which interacts with the differential in an interesting way. So here's what the definition is. So a lambda connection on this Riemann surface C is a pair E comma theta, where E is a vector bundle on the surface, but actually it has a one parameter deformation. So it's really living over C cross A1, where this A1 we think of as having coordinate lambda, once the name lambda connection. And then theta looks like a connection. So it goes from E to omega 1 of C tensor D. But it only sort of sees the differentials coming from C. So it's actually linear over lambda. So it's a C lambda linear map. And it satisfies the twisted version of the Leibniz rule. So the usual Leibniz rule looks like following. So if I did theta applied to a function times a vector, I'm supposed to get f times theta applied to the vector plus df tensor the vector. And in this lambda twisted version of the Leibniz rule, there's a coefficient of lambda in front of the second term. Okay, so it's almost like a connection. So for example, if lambda was 1, this would just be a connection. But if lambda is 0, this term goes away. And what you get is something that's actually a linear map. It commutes with the scalar multiplication action of functions. And so because of this notion, what you get is the following picture. So you have lambda connections on C. You can set lambda equals 1. So you restrict to the fiber over lambda equals 1 on the second factor. And what you get is a flat connection on C. But you can also set lambda equals 0. And what you get is a Higgs bundle, meaning just a vector bundle with an endomorphism like so. On C. So the Higgs bundles are usually easier to understand than flat connections because everything on this side is essentially happening in algebra. It's a vector bundle together with a linear map. There's no sort of nonlinearity in the situation. And so the point I want to make is that the process of passing from lambda connections to Higgs bundles on the curve side is going to be analogous to that object over here. So. But really, it's on D. D is the analog of ZP. Okay, so why do I say this is the analog? A Higgs bundle on a disk is very easy to understand. The cotangent bundle of a disk is trivial. So a Higgs bundle on D is literally the same thing as the vector bundle with an endomorphism. There's no twisting happening. So this guy is the same as pairs E comma theta, where E is a vector bundle on D, and theta is a linear map. So it's a pretty concrete notion to work with if you understand what vector bundles on a disk look like. And so the counterpart to this on the prismatic side is the theorem I wanted to talk about. So this guy, it turns out to be equivalent to something extremely simple. So it's again pairs E comma theta, where E is a vector bundle now on ZP, because ZP is the analog of the disk. So it's just a finite free module over the p-adic integers. And theta is an endomorphism of this vector bundle. It's a linear map. Just like what happens over here, except on the arithmetic side, there's one extra condition this has to satisfy. So such that the generalized eigenvalues of theta mod p. So what do I mean by this? If I have a finitely generated free module over the p-adic integers and an endomorphism, and I reduce it modulo p, I get a finite dimensional vector space over fp together with an endomorphism. So it's an object of linear algebra. And so you can talk about its generalized eigenvalues. The generalized eigenvalues usually live in the algebraic closure because the characteristic polynomial might not have roots over the ground field we started with, but we demand that they do over here. So that's the concrete description of what these Higgs crystals look like. I guess this is due to Drinfeld and also Jacob and myself. It's part of a larger story, but this is kind of the concrete information you get out of a Higgs crystal on spec ZP. It's a vector bundle together with this endomorphism. So I wanted to mention one application of this theorem, which has nothing to do with things I've only defined in this talk. But before I do that, are there any questions about just that table, those analogies? Yeah. If you take A comma I to be ZP comma P, then what is what? Well, A comma I is varying over this inverse limit, so I don't know what it means to fix. If you take X to be spec of ZP, this is actually rather interesting in marrying. So the simplest example is you take X to be spec of FP, and then this invariant is ZP. So what happens in that case is that there's an initial object in this category, which is the first prism I wrote down. For spec ZP itself, what you get is, so these absolute invariants are going to be very closely related to algebraic K theory of ZP. So there's going to be some interesting stuff happening. Other questions? So again, I mean, no, it's fine. Right, so I mean, okay, maybe I shouldn't have given you these complicated definitions. The output is simple, that you have these two categories, and then they satisfy something analogous to what lambda connections satisfy with the complex numbers. And of course, the obvious question you could have at this point is, why would you care about this? I defined something for you in this talk that you didn't know about before, and then I told you it's equal to something simpler. So why care about the more complicated thing at all? It's a fair question. And I have one application that maybe would convince you otherwise. So if you combine that classification I wrote down over there, together with some sort of general stuff on prismatic homology, along the lines of what I was talking about last time, like various comparisons between prismatic homology and Rham homology and so on, what you get is the following corollary. So this was first noticed by Drinfeld. It's extremely simple from the classification over there and some understanding of how these comparisons work. And it's the following. So for X over ZP as before, so smooth projective. There exists a natural endomorphism theta, which is this kind of a Higgs field, or the same kind of theta that's showing up over there, of the de Rham cohomology of the mod P fiber. Satisfying a bunch of properties that I'm not writing out. But this endomorphism is quite interesting. So it's a new piece of structure on the de Rham cohomology of varieties in characteristic P that we didn't know about before. And it's non-zero. In fact, here's kind of the explicit application you get out of it, which is if the dimension of X is smaller than P, then the eigenvalue decomposition of theta gives you the Hodge to de Rham degeneration. So there's a spectral sequence that computes de Rham cohomology in terms of simpler objects called Hodge cohomology. And the spectral sequence does not usually degenerate, but it does in this situation just by the eigenvalue decomposition of theta. And so this is something that was actually known before. So it's a theorem of Deligne-Illusie. And it's rather useful in algebraic geometry in positive characteristic. But I mean, okay, so my personal experience with this is that I remember struggling a lot with trying to understand what was going on in the proof of this theorem in Fine Hall 15 years ago, and feel like I finally understand what's going on, which is that it's really coming from this eigenvalue decomposition for this particular operator, theta. So it recovers the Deligne-Illusie theorem, but it actually gives you a little bit more. So, sorry, some generalized eigenvalue. No, so maybe in that particular case, the theta might actually be semi-simple. So the eigenvalue decomposition gives you everything. But there are lots of examples of varieties where theta is not semi-simple. So the additional structure that you get beyond this decomposition is that on each eigenspace, you get some interesting residual nilpotent operator. And it seems worthwhile to try and study that better. So Petrov recently gave examples where they're non-zero. But I don't think we have like a good theory to understand them yet. Okay, great. Further questions about this? So that was maybe one application of this prismatic stuff. So there's some complicated definitions, but then the output is like this rather simple looking linear algebraic category, and it has some sort of interesting consequences. I want to do something else along those lines in the rest of the talk, but this is going to be related not to the analogy with Riemann surfaces over there, but rather with the analogy with three manifolds. So let me recall how this goes. So part 3. So I think this analogy is due to Mazur or Mumford. And it's sort of less explored or less used, certainly, compared to the previous analogy. But I found it quite useful that it actually led to some rather interesting predictions on the prismatic side. And so, okay, to sort of set the stage over here, I need to give you a definition. So in the definition I gave for prismatic crystals, which I amazingly kept on the board. So there's this kind of inverse limit thing that's happening over these objects of this category. But one thing I haven't exploited yet is that the objects of this category have an endomorphism, the Frobenius endomorphism. There's a phi that's acting on everything. And so it might be prudent to extract some invariant which actually remembers the phi. So for example, these objects are going to have a natural Frobenius action. And we want to sort of remember that in the objects we talk about. So It's not just prismatic crystals, but it's prismatic crystals with an additional Frobenius structure. And so these are prismatic F crystals. So vect phi of X prism O prism is going to be two pieces of data. So E is as before. It's a prismatic crystal in the usual sense. Well, usual for some people. And then phi is some Frobenius structure on this. So, okay, the precise statement is that the Frobenius pullback of E and E are isomorphic to each other, but not quite on the nose. It turns out that requiring isomorphisms on the nose is too strong. But if you bound where the zeros and the poles of the isomorphism can be, so it's a meromorphic isomorphism, then you get a reasonable notion. So they're taking, you allow yourself to have zeros of poles along the vanishing locus of this ideal, which showed up in the definition of the site. Okay, so it just turns out to be the right thing to do. If you've seen Drinfeld's work on the global Langlands correspondence for function fields, you might have seen this condition. It's part of what makes it Drinfeld-Stuka, and that's in fact where this came from. But this is concretely what it is. And so these are the objects I want to now say something about, analogously to what I did over there with Higgs crystals. And I want to do that using this three-manifold analogy. So why is the three-manifold analogy relevant here? Okay, so in this analogy with Riemann surfaces, the point was playing the role of, a spec FP was playing the role of a point. But now we've turned on the Frobenius. So we are somehow remembering the Galois action. And the absolute Galois group of FP is not trivial, right? It's essentially the integers, or it's some completion of the integers. So from the point of view of Galois theory, a finite field feels more like a circle rather than a point. And so that's the starting point of this analogy with three manifolds. And so it goes as follows. So again, I'm going to make another little table. So, right, you have spec FP over here. I said that this corresponds to the circle, S1. And then I think it was Mumford that observed that if you think of the circle as really a knot embedded inside a three-sphere, and then take a little tubular neighborhood of the knot, you get a pretty good analog of spec ZP over there. So think of this as a knot K, and then M is going to be, so this is a knot, and this is a tubular neighborhood, and a three manifold. Let's say just an S3. So the contention is that this is a good analog of spec ZP. And in this analogy, if you look at the boundary of this tubular neighborhood, I mean, if you're just picturing like a circle inside three space and then you fatten it up and then you go to the boundary, you get a torus. So this is in particular, it's a Riemann surface. It's just a torus, but okay, let me call it a surface. And the analog of that operation on this side is inverting P. So passing to the boundary, so it's spec of the p-adic numbers, so QP rather than ZP. And so this is kind of how the analogy starts. And so, as I said, one of the reasons this is a good analogy is that phi1 of the circle is Z, and on this side, phi1 of spec FP, as Grothendieck defined it, is the Galois group of FP bar over FP, which is a completion of Z. So modular issues of profinite completion, they have the same fundamental groups. What we're going to be interested in is the notion of local systems on the remaining two objects in the picture. So first, let's talk about the theory that's better understood. So the boundary over here and QP over here. So log FP of this. So what do I mean by this? I just mean the collection of all local systems on this Riemann surface with coefficients in the finite field FP. So if you like, it's just representations of pi1 of this Riemann surface. And I want to do it with mod P coefficients everywhere. So it's a rather simple object, but let me just give it a name. Like in our case, this is just a torus. So to give such a representation, I just had to give two commuting matrices, mod P, because pi1 is Z cross Z. And the analogous thing over here, you can either take it as a definition, or if you know some other definition of the left-hand side, it's going to be a theorem. That this is mod P representations of the absolute Galois group, QP. So the kind of thing that you might care about in number theory. And so, okay, so far I've given you one piece of evidence that this was a good analogy, which was just pi1s over here matching up with pi1s over here. Here's a better reason to think of this as a good analogy. So here's Poincare duality on this side. And I'm going to do Poincare duality on the Riemann surface, so on the boundary. And so the natural coefficients for cohomology are local systems, as I was saying before. So let's pick an object there. So if E is a mod P local system on this surface, then Poincare duality says that HI with coefficients in E, if you dualize it, it's naturally identified with H2 minus I with coefficients in E dual. And if you're an arithmetic person, you want to put a Tate twist there. So let me put it, but you can ignore it. It's a twist by one. And so this is just usual Poincare duality on a Riemann surface, stated in some rather exotic looking form. And this has an exact counterpart on the arithmetic side, which is Tate duality. So it's the exact same statement. So E is a, let's say, I think of it in terms of a representation. So if E is a representation of GQP, then Tate proved that for Galois homology of the absolute Galois group acting on such representations, you have an analogous statement. HI GQP E dual is H2 minus I GQP E dual 1. So literally just took the same symbols and copied them over. Okay. And right, so maybe one thing I should emphasize is that on the arithmetic side, you cannot ignore the twist. The twist corresponds to roots of unity. And roots of unity carry a non-trivial Galois action. So on this side, you cannot ignore the twist, even though we could on this side. And this causes some complications in what I'm about to say. But I think this was kind of, so this is the classical story. And I think in the original Maser-Mumford picture, there was sort of another layer to this analogy where you actually talk about the global object, not just these local objects. And then there's global duality, which fits into the picture. But I don't want to do that. What I want to do is I want to explain how this and this are analogous. So far, I've just told you stuff about the outer pieces. All right, are there any questions so far? Just feel like I'm talking and talking. Right, so I'm repeating what Chris said, that for the people on Zoom, you can unmute yourself and ask a question, and then it will boom through the auditorium. All right, so where am I going with this? Right, so because of this duality theorem, you get some interesting structure on the space of local systems on the Riemann surface. If you sort of define such a space correctly, the tangent space to a point is going to be controlled by, so a point of the space of local systems will be a particular local system. And the tangent space to the point corresponding to that local system will be given by a cohomology group of not quite the local system, but rather its adjoint version. And so you can imagine that this kind of theorem tells you a little bit about the space of local systems. And it does. What it tells you is that the space has a natural symplectic structure. So over here, what you get is that log fp of the boundary has a natural symplectic structure. And I want to talk about what the counterpart to this, or some consequence of this, would mean on the arithmetic side. Okay, so I just mean that at every point you're going to have like a symplectic vector space corresponding to the Poincare duality pairing. Okay, right. So far I've just talked about K and the boundary, and so now let's bring in M. So on the topological side, there's a theorem. I don't know who this theorem is due to. I found a paper of Dan Fried where he talks about it, and he also attributes it to Lisa Weeks and someone whose first name is Jeffrey. But it's the following statement, which is, I think, easy to prove in this particular case. So I can take mod P local systems on the 3 manifold, which is in the middle, and I can take a local system here and restrict it to the boundary. So this operation of restriction from the left to the right is a map of spaces, because I'm thinking of these as spaces now. That's what the underline means. And the statement is that this is a Lagrangian map. So if you ignore some issues with singularities, what this is saying is that the left-hand side is a Lagrangian submanifold of the right-hand side. So at the level of tangent spaces, the tangent space on the left gives you a maximal isotropic subspace of the tangent space on the right, which has a symplectic structure. And so I want to talk about the counterpart to this statement on the prismatic side. Okay, so yeah, I think my timing will work out, but are there any questions so far? Okay, so first of all, we need to just talk about the restriction map. So we need a way to go from FP local systems on M to the boundary in the arithmetic side. One thing, okay, so the notion of FP local systems on M, I guess I should have said this. So mod P local systems on spec ZP, I'm trying to convince you that prismatic F crystals is a good notion of a mod P local system on spec ZP. So on this side, I have prismatic local systems, prismatic F crystals on ZP, which is this kind of object. And it's actually not clear how you go from here to the analog of the right-hand side, which is mod P representations of the Galois group. But this exists. So let me call this construction T. So this was in my work with Schulze. It's not super hard, but just don't want to go into it. So there's an operation that takes an F crystal on spec ZP and extracts a local system on the generic fiber, analogous to how you can take a local system on the manifold and restrict it to the boundary. And then the theorem, which is analogous to this theorem, is the following. So let me put a star over here, because it's work in progress. So meaning it's not fully written. But it states the following. So okay, actually, you know what? I'm not gonna. This is the last thing I'm gonna say, so I can just end the table. So for a prismatic F crystal E, on ZP, we want to say something like Lagrangianness, except as I said before, this doesn't make any sense because there is no symplectic structure on the target because of the Tate twist. The Tate twist means that you don't the objects aren't self-dual, they're only self-dual up to a twist. And that causes, you can't literally say that it's a symplectic object, but you can still make sense of the following statement. So for prismatic F crystal E on spec ZP, the natural map from the cohomology of something to the Galois homology of its, so from the cohomology of the F crystal to the Galois homology of the corresponding representation is the exact annihilator of the corresponding map on Tate duals. So the Tate duals are defined by dualizing the crystal and then putting in a twist. And so this is the statement that you get with the following explanation for what the double prime means. So this object over here, so it's defined by Drinfeld. It's non-trivial to define the correct notion of cohomology for prismatic F crystals, but Drinfeld came up with a very beautiful recipe. And so this is some arithmetic analog of the statement that the map from the cohomology of local systems on M to that of its boundary is a Lagrangian subspace. You can't quite literally say the same thing, but up to duality, this is what we get. Okay, so I have 2 minutes. I wanted to say a little bit more about what this is useful for, so for experts, but maybe I'll just say it in words. Okay, so this is cohomology of mod P Galois representations. For cohomology of mod P Galois representations, Bloch and Kato had defined a certain subspace called the Bloch, well, it's used in the definition of the Bloch-Kato-Selmer group. It's sort of the crystalline part of cohomology. Their constructions only work with rational coefficients. And so what I'm trying to say over here is that this theory provides an integral analog of what Bloch and Kato were doing. It's an integral notion of the crystalline part of Galois homology, and it seems to satisfy the desired properties. And so my secret hope is that this is useful in understanding deformation theory of mod P Galois representations better. But that's a far out dream at the moment, and I'm out of time. So let me just end here. Yeah, so I haven't checked it, but I would conjecture that. So there's a ZP analog of the statement, and then I would conjecture that what I'm defining over here when you invert P is exactly what they define. But this is not known. Well, as I said, this is barely known, so. But I mean, it's going to be true. Yeah. Yep. Yeah, good question. So I guess I was a little sloppy in what I wrote. Really, since I was working, I should have said ZP over here because I didn't reduce mod P on the left. I could either reduce mod P and then go to mod P representations or work integrally on both sides. And so what Peter and I proved in this paper where we defined this functor is that this functor is fully faithful and the image is exactly ZP lattices in crystalline Galois representations. So at the level of categories, it's sort of, that was some evidence that this is giving the right thing. And now I'm saying at the level of homology, it's also seems to be working. Yes, right. I think this gets used in this proof of the Tate conjecture I mentioned on Wednesday. So Kissen defines these abstract functors that take lattices and Galois representations and produce F crystals. And you want to know that in geometric situations, if you take the geometric lattice on the Galois side, what you get is the geometric crystal on the F crystal side. And this kind of structure allows you to prove that compatibility. So I think specifically for K3 surfaces, in Kersig 2, this is new.
Can you say a word about proving this corollary?
Can I say a word about proving this corollary? So, okay, the endomorphism just comes from the fact that the way this formalism works is whenever you have, do I still have this? Okay, yeah. So whenever I have some x over spec ZP, I can push forward the constant sheaf, and I get a prismatic crystal on spec ZP. Then I get a Higgs crystal on spec ZP. And then I can go through this equivalence to extract a module with an endomorphism. And that module with an endomorphism, reduced mod P, turns out to be the Rham homology through the comparison isomorphisms for prismatic homology. So that's one thing you need. And then the other thing you need, which is a calculation, is that this endomorphism preserves the conjugate filtration under Rham homology. And moreover, theta acts by minus I on I forms. So if the dimension is smaller than P, then the eigenvalues that show up on the I forms for different values of I don't talk to each other. And so you get this decomposition. Yeah?
So, are you why
am I going to explain what?
Are you going to explain why phrase from hot phrases?
Peter's question from before. Right, so, okay. Prisms are, okay, so I think the original intuition was something like the following. So here's spec A for this prism. Here's a face of the prism. It's a divisor on the prism, so it's spec of A mod I. X lives over spec of A mod I usually in applications. So here you have X going in, and then this machinery outputs a cohomology theory that lives over all of spec A and has different sort of, there's like hot state cohomology, there's the Rham homology, there's crystalline homology, there's italic homology, and so on. And so that picture looks like the picture of a prism. It also happens to be closely related to the picture of one of my favorite albums. Wait, sorry. In the real world, you cannot build what from what?
I can. So if I have some crystals, I can cut it to make a prism. So it's the etymology, right? Like the crystals in.
You're asking why crystals? Well, not directly. So Grothendieck had this idea of defining crystalline homology. And so to him, a crystal was something that's rigid and grows, is what he said. And so the prismatic crystals are just the generalization of the Grothendieck's notion of a crystal to the prismatic site. Yes. Yeah. I think people are trying. So Petrov, in his example, where he proves this thing, gives an example of something that's non-semi-simple, gives a sort of classical interpretation of the first obstruction to semi-simplicity. So essentially, the dimension is P, and if you break it up into the generalized eigenspace decompositions, I forms are not going to contribute anything for I not equal to 0 or P. So you just have functions and P forms. And there's some interesting map from P forms to functions. And Petrov explains how to interpret this in terms of the failure to lift Frobenius to Z mod P squared and some other piece of purely homological input. So yes, I'm saying there's an example where you can interpret it classically, but I don't know sort of a more general statement along these lines.
Find the Zoom audience if they can ask questions. That would have been fun because of voice.
No, it's okay. It's Friday evening, probably. There are better things to do.
Well, if there aren't any more questions, let's Bhargav and remind you all that we'll be back on Monday for the third talk.